250 miles up, the environment is actively trying to kill you. You are exposed to a hard vacuum, relentless solar radiation, and microscopic debris traveling at 17,000 miles per hour. Down on Earth, if you want to build a laboratory, you pour a concrete foundation, set up a few cranes, and drive fleets of flatbed trucks straight to the site. In orbit, every single one of those traditional methods is physically impossible. The core obstacle is the planet itself. Earth pulls everything inward. To launch even a single ounce of raw aluminum or a liter of water off the surface requires an immense, highly expensive expenditure of chemical energy. But once a rocket expends that energy and reaches the flat plane of low Earth orbit, the physics flip. Vertical thrust is replaced by horizontal velocity, allowing multi-ton payloads to float effortlessly. Because of this severe launch penalty, putting a station in space requires an entirely different approach to engineering. It demands a system of extreme zero-gravity logistics. The solution to the gravity well is modular architecture. Instead of launching one impossible, massive structure, you launch a series of smaller, self-contained pieces. Over a span of years, these separate pieces are flown up one by one. To make this work, every single module must be designed with standardized, universally compatible connection points. You can see this system actively functioning right now. Look at this central hub, where 2 commercial spacecraft are currently locked into standardized docking ports. These visiting ships do heavy logistical work. They fly up on regular schedules to drop off fresh science racks, pressurized oxygen tanks, and replacement hardware for the crew. These nodes operate as continuous biological arteries. They keep the isolated crew supplied, powered, and alive. Delivering the pieces to orbit is only half the job. Once a massive 15-ton habitat module arrives, it still has to be pulled out of the cargo bay and attached to the station. In a frictionless vacuum, human muscle cannot safely arrest the momentum of an object that size. It requires automated, heavy-duty infrastructure. This is where the station relies on its heavy lifter. A segmented, articulated robotic arm extends outward and locks onto the incoming cylindrical supply ships. Driven by internal motors, this arm acts as the primary construction crane. It can grip a multi-ton module and inch it into its final structural position, operating continuously without needing oxygen or experiencing physical fatigue. Without a specialized robotic crane capable of gripping and moving these massive exterior components, expanding the station's footprint would be mathematically and physically impossible. But large robotic cranes lack tactile feedback. They can place a module against a docking port, but they cannot thread a bolt or connect a fluid line. To finalize the assembly loop, astronauts have to put on pressurized suits and step outside into the vacuum to perform spacewalks. This requires a complete integration of human and machine. Here, an astronaut is anchored directly to the end of the robotic arm, relying on the heavy machinery to transport them safely to their worksite. Once in position, they execute the highly intricate tasks. They manually drive specialized bolts, route external power cables, and lock down ammonia coolant lines. Even with billions of dollars invested in automated robotics, the assembly relies entirely on the fine motor skills and real-time problem-solving of human hands. When you look at the complete system, the standardized supply ships, the robotic cranes, and the spacewalking crews working in tandem, you are looking at a fully functional orbital spaceport. Perfecting this 3-part logistical chain is a mandatory prerequisite. Before we can build outposts deeper in the solar system, we had to prove we could build them here, close to home. Right now, aerospace engineers are taking this exact modular blueprint and applying it to the next generation of off-world architecture. We are already seeing the conceptual phase for the Lunar Gateway. Hardware contractors are mocking up these curved, modular habitats designed specifically to be assembled in orbit around the Moon. By staging and connecting these modules in a lunar orbit, engineers can build a deep space transfer hub, a place to refuel and resupply crewed vessels without dragging them all the way back down into Earth's gravity well. The mechanics of modular assembly have allowed humanity to permanently occupy low Earth orbit. Now that same engineering framework is the literal stepping stone required to reach our next destination.